Welcome back, students, to the lecture on nuclear physics. This is the second lecture, part 1. In the last lecture, we went through the Rutherford scattering experiment, which led scientists like Rutherford to deduce that the nucleus is actually a very small, massive, and charged particle. So its size is about 10 to the power of minus 15 meters. And if you imagine the atom as the size of a football field, then the nucleus, where all of the atom's mass is concentrated, is actually only the size of a pinhead. So that's how small an atom is, a nucleus is, compared to the size of an atom. We also noted that the nucleus has a very large positive charge. It is as large as the charge of all the protons that are on the atom, right? And they all reside inside the nucleus. So this makes them a very small but concentrated targets for the alpha particles to collide with. We also discussed some other additional properties. Inside the nucleus, we find protons and neutrons bound tightly together, and we can tell the type of element from the number of protons that are in the nucleus. Right. In today's lecture, we're going to discuss what happens when we launch particles towards one another, basically producing nuclear reactions. And one quick way to define nuclear reactions can be as the following. A nuclear reaction is a process by which two nuclei, or a nucleus and a subatomic particle, collide to produce one or more new nuclides. So I've shown three examples of nuclear reactions here on the slide. The first one is called fission, which we will talk about in the third lecture. In fission, a heavy element is broken down into lighter new elements. So a heavier nuclei is broken down into nuclei that have a smaller mass number. So basically big piece into small pieces. Right? In fusion, right, we get smaller nuclei with a smaller mass number, combining to form nuclei with a larger mass number. In this case, we're taking two isotopes of hydrogen, deuterium and tritium, and reacting them to produce helium. Right, this process here, called the triple alpha process, is a very important process to you and I, because this is the primary process in which the universe produces carbon. Carbon that is found in our bodies, right? In all the carbon-based elements, all the hydrocarbons, and all the other compounds that have carbon within them. For example, carbonated water, right, like Coke. So this is a very important nuclear process to life itself, and it turns out that this is actually a very special process because in most of our nuclear reactions, we actually consider two particles interacting. So for example, in the fission case here, we have a neutron interacting with a uranium nucleus, and in the fusion reaction, we have a deuterium particle interacting with a tritium particle. But in the triple alpha process, this is as close as we get to a three-particle collision. So it's not that three-particle collisions are impossible, it is just that the probability of them happening is exceedingly small because the interaction times for particles are extremely small already. So to have a third particle come in together is low probability. So in this triple alpha process, it's quite interesting. We have an alpha particle and another alpha particle combined together to form a beryllium nucleus. But this beryllium nucleus is what we call metastable. So it is in a state where it exists stably, but only for a very, very tiny fraction of time. It is very unstable compared to stable nuclei, like the rest of the elements that we see in everyday life. But it is relatively stable compared to something that would break apart instantly. So this gives it sufficient time for the probability of a third alpha particle coming in to collide with it and producing yet a second nuclear reaction, giving us carbon-12. So this actually happens in the shells of very large stars. So for example, in our sun, this actually doesn't happen because our sun has a fusion process that converts hydrogen into helium, but not helium into carbon. So this is what we are going to apply our knowledge of nuclear reactions to. We'll see how nuclear reactions can be used in the case of fission and fusion, and some specific examples of nuclear reactions that can be found in nature. Alright, so much like chemical reactions, we need a way to represent nuclear reactions, right? So we can use an equation a nuclear reaction equation where the nucleon number and proton number are able to be balanced on each side. So it looks a bit like our chemistry equation. It's just that in this case, the elements themselves are not conserved. In a chemistry reaction, you don't have nitrogen turning into carbon or so on and so forth, right? So in this case, we are describing a reaction where a neutron is incident on a nitrogen nuclide, and this nitrogen nuclide then becomes a isotope of carbon, a carbon-14 nucleus, and emits an additional proton. So if you take a look here, you can start to get a hint of what we will be doing in the rest of this topic. Basically, we'll be checking out the conservation laws for nuclear reactions. There's actually also an alternative way of noting nuclear reactions, and this is called the symbolic expression form, and it looks like this, where we first have the initial nuclide, the incoming particle in brackets, followed by the outgoing particle, and the final nuclide that has been transformed. Right? So of course, nuclear reactions don't have to be in the case of two particles becoming two particles. It can be two particles becoming three or more particles. It is possible. For example, in the case of the fission reaction of uranium in the previous slide. Right? So this first method in which we note down the nuclear reaction, okay, is the more common notation used by Cambridge. So you generally find this notation used in A-level questions and in our tutorials. So do take a look at some of them during your practice. Alright. Now, the most important thing that we need to do for the kinetics of nuclear reactions is we need to know the conservation laws. So we have learned a lot of conservation laws in physics. The most important of which is conservation of momentum and conservation of energy. So for atoms, things are a little bit different. So let's go through them one by one. There are 4 here, and these 4 you must be able to remember them for exams. First is the conservation of nucleon number. So in the conservation of nucleon number, the total sum of the mass numbers on both sides of the equations should add up. So in the previous slide, we had the mass number on top here. This is the mass number. For neutron, it's 1. For nitrogen, it's 14. You can see that it adds up, and the total is 15 on the left-hand side. On the right-hand side, the total is 15 as well. So that's our first conservation rule. The second conservation rule is the proton number. Basically, the proton number represents the amount of positive charge there is on all the particles. So in the previous case, we have 0 for the neutron and 7 protons in the nitrogen nucleus. So on the right hand side, we must also have a total of plus 7 for the sum of the proton numbers. So for the carbon, there is 6 protons, and the outgoing proton has 1 more proton. So the total gives us back 7 again. Now the proton number may seem like it's an arbitrary rule, right? Why must we conserve the amount of protons? Basically, this boils down to a more fundamental rule of the universe, which is actually we must conserve the amount of charge in the universe. So you can't create or destroy charges, right? And how it manifests in our calculation is that the sum of atomic numbers on both sides of the equation must be the same, atomic or proton numbers. Okay, the third one here is something that is no stranger to all of us. Basically, even in a nuclear collision where my nucleus changes from one type of element to another, or the total number of protons and neutrons changes, or the total number of particles change in the first place, right? We still must conserve momentum. So it seems like momentum is this overarching rule that can't be broken. It's conserved in elastic collisions, it's conserved in inelastic collisions, it's even conserved in cases where there's light that you have learned about. So in this case, the linear momentum of all the particles in the system must be conserved. So if I add up all the momentum on the left hand side of my equation, and that must be equal to the sum of all the linear momentum of the particles on the right hand side of my equation. And of course, we're talking about momentum, so it's vector sum, not scalar sum. Right, the last one is something new for us, but I'm sure many of you have heard this phrase before, E equals to mc squared, this equation. And of course, it was coined by our very famous Albert Einstein. And this one, unlike photoelectric effect, was derived from what he's famous for. Einstein is famous for relativity, right? So E equals to mc squared is called the mass energy equivalence, which we'll be talking about next. But let's quickly recap the conservation law. Normally, we would say that the total energy of a system is conserved. So even in an inelastic dynamics collision, total energy is conserved. It's just that your kinetic energy might have become other forms of energy, like deformation energy. But we still want to say that the total energy of all forms of energy are conserved. But what we have never considered is, what is the role of mass? Can mass go missing in the universe? So it turns out in nuclear reactions, we can have missing mass. And this actually allows us to take that into account when we start to say that, hey, if mass and energy are interchangeable, then instead of just conserving energy and conserving mass, we will conserve the total amount of mass energy in the system. Right, so with these 4 conservation laws, we are able to solve kinetic equations for nuclear particle collisions. Right, so let's talk a little bit about Einstein's mass energy equivalence. So let's lay out the principle of conservation of mass energy, which is a modification of our principle of conservation of energy. Basically, Einstein says that mass and energy are interchangeable, and the total mass energy of a system must remain constant. So this must mean that, hey, if mass and energy are interchangeable, then when some mass is created, some other form of energy must vanish. And when some mass is destroyed, some other form of energy must appear. So the equation that leads us to that is delta E equals to delta mc squared. And this is actually the original formulation that Einstein initially had. So it wasn't that any mass is worth energy. It was when mass goes missing or when extra mass is created, the total energy of the system must change correspondingly as a result. So that the total amount of energy, which is equivalent to the mass created or destroyed, is also taken into account of. Of course, the units for energy and mass are not consistent, right? So we can't just say mass changes into energy. So the equation has an additional constant term, c squared, which is the speed of light. Of course, Einstein later on generalized this to take into account any object with mass, right? So breaking this equation down, let's recap a little bit. Mass can be created or destroyed, and that's taken into account with delta m over here. And delta E will be the equivalent amount of energy that would disappear or come into being because of that mass being created or destroyed. Right? So in some specific cases, we can talk about how an object would change its mass. So an object experiencing one of these will experience a change in its mass. So first, if an object were to accelerate, right, it would gain Ke. Now gaining Ke would change its mass, right, because now it has an additional form of energy. Its total energy has increased. So by the mass energy equivalence, we would say that his total mass has increased as well. There are other factors that can give a body energy. For example, bulk potential energy, for example, being in a gravitational or electric field, or increasing or decreasing a gas's internal energy. Now, just like to take note here before you all get confused. When I say an object changes its mass when we accelerate it, what I mean is this object's relativistic mass increases. So, when Einstein mentioned about mass energy equivalence, okay, there's 2 definitions we need. One is called mass, and the other is called rest mass. So we want to define something called rest mass first before we talk about mass. When an object is at rest and isolated, means it has none of these other forms of energy, okay, that mass is called its rest mass. So you and I, we all inside the gravitational field right now. So the mass that we measure, even if we're standing still, is not called our rest mass because technically we have some kind of bulk PE, right? So if we were to take our body and move it all the way to infinity away from any position in the field, and then also not accelerated, okay, and we start to measure our own mass, okay, using a mass balance that is not moving with respect to us, okay, then what we would measure is our own rest mass. So the masses of particles that we quote within the questions in A-level, these are the rest mass of the particles. So of course, if I give a particle other forms of energy, it would have more energy. It will also have a larger equivalent mass. We call that other mass the relativistic mass. Okay? So just note that most of the time when we refer to a mass of an object, we're referring to its rest mass. Now, how how does mass relate to equations and reactions, right? Our nuclear reaction equations. So it turns out that in chemical reactions and physics reactions, okay, nuclear reactions, energy is created or destroyed in a sense, right? For example, in a chemistry reaction, we could produce heat enthalpy change, right? Now, this enthalpy change has been produced, and it obviously we know it comes from certain amount of potential energy relationship between the bonds in, for example, the compounds, right? This must also mean that some of the apparent mass of your compounds has changed, right? So how does it appear? How does it work? Like, for example, when we did chemistry reactions, we never ever bothered measuring the masses of the reactants and products and saying that, hey, they are different, right? In fact, we do assume that the mass of the products and reactants in chemistry reactions are the same. So it turns out for chemistry reactions, because the amount of energy that is produced in chemistry reactions, chemical reactions, sorry, is actually very, very, very small. So that amount of energy, when you divide it by c squared, okay, gives you only a very, very tiny fraction of mass loss. Okay, so we are actually not very aware of this. But of course, now we are aware of it, it's measurable. Okay, in nuclear reactions, however, the mass loss can be pretty significant and a large amount of energy is created. So this is the basis of how nuclear reactions produce energy. So in general, nuclear reactions give the range of mega electron volts of energy. Whereas for chemistry reactions, it's in the order of magnitude of EVs, right? So before we proceed further, let's do a quick unit check to make sure that our E equals to mc squared is dimensionally consistent. So E equals to mc squared. On the left hand side, we will have energy, and the unit of energy is joules. Okay, and on the right hand side, we have mc squared. So m is mass, so we have kilograms, and c squared is meter square per second square, speed square basically. Right, one way of getting energy is by calculating work done, right? So I can use work done to find the units of joules. So for joules, it's just Newton meters. And Newton is the unit of force. So the unit of force can be represented with MA, mass times acceleration. So kg meter per second square. So if I put these together, kg meters per second square, multiplied by the mass from W equals to Fx, you will get kg meter square per second square, which is dimensionally consistent with mc squared. Okay, so this means that our dimensional consistency, the units, check out for E equals to mc squared. Obviously, it doesn't mean that the equation is valid. To do that, we will need to do experiments to double check that it is indeed equal to mc squared and not some other constant or with another proportionality constant. But there's enough experiments that have been done to verify that it is indeed just mc squared. Okay, let's take a look at one example and do some calculation for mass energy equivalence. So we know that the mass of a nucleon is roughly 1 U, right? Find its energy equivalent in mega electron volts. You may pause the video here and try to do this calculation on your own, but if not, I'm going to proceed. So we can use E equals to mc squared. On the right side, we need to substitute in 1 U of mass as delta M, right? So 1.66 times 10 to the power of minus 27 kilograms is U, the unified atomic mass. And then we'll multiply by c squared, speed of light squared, giving 1.49 times 10 to the power of minus 10 joules, a very small amount of energy. But if you convert it to electron volts, you divide it by E, you'll be able to get 900 mega electron volts. So it'll be quite convenient to remember roughly, if I were to take a nucleon and make it disappear, the amount of energy I would get is 931 mega electron volts. Obviously, generally, we can't do that because we have to conserve nucleon number. So we'll take a look at where we can make mass disappear in nuclear reactions. Okay, but before we go to nuclear reactions, let's talk about regular physics reactions, okay, or regular physical processes. So one such process we know is the heating of water. Now, heating of water causes energy change, right? So first we can calculate how much energy change is required to raise the temperature of 5 kg of water. So 5 kg is roughly, like the size of catering food, right? So, and catering food is mostly made out of water. So this is roughly the energy for heating objects up. So from just 20 degrees to 70 degrees, let's calculate this. So using E equals to mc delta theta, okay, our energy, our formula for heat and heat capacity, we find that for 5 kilograms of water, for this 50-degree C energy temperature change, we will require about 1 megajoule of energy. Okay, 1.1 times 10 to the power of 6 joules. Let's calculate the corresponding equivalent mass increase in water. So if I want to find the corresponding mass equivalent, I need to use E equals to mc squared. I'm going to substitute E as 1.1 times 10 to the power of 6 joules to get the mass. So doing our calculation, we actually get 1.2 times 10 to the power of minus 11 kilograms. That's a fraction of a fraction of a fraction of a milligram. So basically unmeasurable in everyday circumstances. So when we do heat objects up, when we give them energy, their apparent mass seems to increase. Their relativistic mass increases. Of course, the rest mass of water is still the same because the rest mass of water is a defined quantity for water that is, not moving and has no other forms of energy. So when we heat it, we're actually giving it another form of energy, thermal energy or internal energy. And this is why there's an extra increase in mass. So when an object gets more energy, it also apparently increases in mass. Okay, so compared to the mass of the water itself, which is 5 kg, this change in mass is actually too tiny to measure. Okay, before we go on to the next part of the lecture, just like to answer one of the questions that some of you all might have been thinking about. So a nucleus has positive charges. Why does the positive charges in a nucleus, the protons, not fly apart? After all, they do have electrostatic repulsion, right? And another question is the neutron has no charge. So why does the neutron stay attracted to the protons in the nucleus? In fact, why do they even stick together in a nucleus? There's no reason if they have no force keeping them together, right? So that answers this question. Why do nuclei fly apart? So it turns out there's an additional force that you have not learned about, and it's not in syllabus, that's why it's called enrichment. And this additional force is called the nuclear strong force. Okay, and the nuclear strong force is a force that acts between the particles that make up the protons and the neutrons. So if you thought that the protons and neutrons were elementary particles, okay, you didn't watch my Kurzgesagt video that I linked for the last lecture. So in the last in that video, it explained that the protons and the neutrons are actually made up further of smaller elementary particles called quarks. And the quarks have a force that attracts them to one another to keep them within the proton. Okay, and that force is the strong nuclear force. So the attractive force between quarks is called the strong nuclear force. So we have learned about we have learned many different kinds of forces. Generally, they can be reduced to the 3 different kinds of forces we have now talked about so far: electromagnetic forces, gravity, and now we have the strong nuclear force. It's called the strong nuclear force because there's also a weak nuclear force. The weak nuclear force governs reactions that for radioactive decay, and Mr. Halim may or may not talk about it. But if you're interested, you can go and ask him. Right, so in the strong nuclear force, okay, there's some residual forces left behind. So the neutrons and the protons also have an attraction towards one another. So you can take an analogy from chemistry. Within a molecule, okay, it is the electron bonding pairs, like covalent bonds, ionic bonds, that give you the attraction between the atoms that form the molecule. But molecules also can affect one another, right? Through maybe processes like van der Waals or maybe even ionic forces. So it's sort of like a leftover electric force from the electron that gives it that kind of attraction. So that's an electromagnetic version of the strong force. So in the strong force, actually the force is between the particles making up the protons, and that leftover force, some of it allows the protons and the neutrons to attract one another. So on the right hand side here, you can see a nice graph that we have plotted the force between the neutrons. So of course nucleons. So the nucleons, the protons and the neutrons, are at an equilibrium distance from one another. If the strong force wins, the attractive force wins, then they will come even closer together. But if the repulsive force between the positive charges wins, then they will be pushed further apart. So there must be some kind of equilibrium for them to exist at their current nucleon separation. So this one, the units is /fm. Fm is for femtometer, 10 to the power of minus 15 meters. Right. So you see that this is our inverse square law for electrostatic repulsion. That's something we have already learned. So the strong force is much stranger. The strong force is a force that disappears with distance very quickly. So we think it's actually to the power of 3. So it doesn't obey inverse square law. But it becomes very strong, right, at short distances. Then when you try to squeeze it even shorter, it becomes repulsive. So it's kind of weird, right? It's a very complicated field to study. If you are interested in it, you need to be a physics major in university. Alright? So the strong nuclear force actually binds the quarks together. So this is a picture of a model of what a proton could look like inside. And you can see inside the proton there's actually the up quark, and a down quark. So these are the subatomic particles that make up a proton, right? And the 3 of them are kept together with this like spring looking bond here. We call this the strong force gluons. So gluons are the imaginary particles or particles that keep the quarks together, right? So they're called gluons because they're named after glue, right? So interestingly, gluons function a little bit like particles in a sense, and to have this force it's a little bit interesting and complicated. So if you have enough already, you can just skip to the next lecture. But for those of you who are interested to listen, the gluons themselves have like charge. So you know the electron and protons electric charge. For the electric force, there's positive and negative charges, right? And then for mass, you have only positive mass. You don't have negative mass. So if you look at gravitational force, you only have mass, one type. No negative mass, only positive mass. Then when you get to the electric force, it's a little bit more complicated. You have 2 types of charge, positive and negative charge. So that's still mathematically easy to handle. When you come to the strong force, which is the gluon force, okay, things get more complicated. We got 3 types of charge. So instead of calling one plus, minus, and some other new thing, we just use the word color to represent them. So red, green, blue. That's why our quarks are colored in red, green, blue. So in order for the charges to neutralize one another, the color charges to neutralize one another, you need one red, one green, one blue. So that's why the quarks arrange themselves in 3s inside a proton. So one of each color, right? And also the gluons will have the colors as well, right? So you need one of each color to cancel each other out to get back neutrality. So if you also paid attention to this diagram here, you can see that the arrows are drawn with rainbow colors to represent the color force. So we call the strong force the color force. And the field of study of the strong force is called chromodynamics, right? Named after color. So okay, we did overrun our time for this lecture, but I hope you have learned something new and something interesting for you.